24 rabbits were released into the Australian wilderness during the 19th century, and within a remarkably short period, these few animals nearly decimated the ecology of an entire continent. Why did China choose to gather 1,200,000 of these very same creatures exactly 100 years later to serve as a primary tool for environmental restoration? It seems impossible that a biological plague could function as the secret mechanism behind a $10 billion economic engine. But in reality, this strategy became the foundation for a massive industrial transformation. One can notice how engineering has systematically converted environmental chaos into a precise logistical order. 41% of the surface of the Earth is already classified as desert. Almost half of the global landmass consists of biologically dead Earth, while another 40% remains in imminent danger of being swallowed by advancing sands. Humanity focuses its efforts on preserving the remaining forests, yet China has been forced to confront a silent but brutal internal crisis. 27.4% of the entire Chinese territory has been severely affected by the process of desertification. This represents a colossal physical area, equivalent in scale to almost 4 times the size of the state of Texas in the United States. The epicenter of this geological disaster is located within the Kubuqi Desert. At first glance, this region appears to be a wasteland of shifting dunes, but it serves as the testing ground for a massive technological intervention. The process is only gaining momentum as machines move across the sand. It is visible how the landscape shifts under the weight of heavy equipment. This is not a common geographical location, but a harsh geological environment where the sand once moved relentlessly. One can notice the camera gliding over the vast expanse of the Kubuqi, where the heat creates a shimmering distortion above the dunes. A giant horse made of glass and silicon has been constructed here, and its massive frame is clearly visible from space. Everything only gets more complicated as the scale of the infrastructure increases. This structure connects the biological management of animals to the generation of renewable energy. The project does not end at this stage. It represents a transition to the next level of land reclamation and industrial profit. From here, the transformation moves to the next phase of processing as the desert is systematically reclaimed. Minus 20 degrees Celsius is the temperature to which the thermometer plunges during the brutal winter months in this region. Why did a once fertile landscape transform into a lethal wasteland of shifting dunes? It only looks obvious that nature follows a fixed cycle, but in reality, a delicate environmental balance was shattered over several decades. The desert of Kubuqi expanded more than 40 kilometers toward the east, erasing the green pastures, flowing rivers, and thriving villages that historical records once documented. The wind dives with the intensity of a mechanical turbine, carrying grains of sand that strike the skin with the sharpness of metal knives. One can notice how the landscape shifts between two extremes, as the winter freeze gives way to a summer heat so scorching that it physically burns the surface of the soil. The grass disappeared as the wind grew in strength, allowing the sand to begin its relentless movement across the plains. Large-scale ecological degradation turned the Earth into an entity that seemed to swallow homes and infrastructure from beneath. But this is just the beginning. 60 meters is the height of the massive sand dunes that advanced over the territory, reaching a scale equivalent to a 20-story building. These geological giants moved across farms and vital transport arteries, burying everything in their path under millions of tons of silica. The process is only gaining momentum. Statistics show that 20 million tons of food were lost annually to this encroaching sea of sand, creating a catastrophic event that unfolded in slow motion. The government implemented a series of rigorous technical interventions to halt the progression. Engineers drilled deep water wells, and authorities established a strict prohibition on livestock grazing to protect the remaining vegetation. They constructed physical barriers and planted defensive lines of trees across the desert fringe. It seems simple to block the path of sand with a wall of plants, but in reality, the desert continued to advance despite these efforts. The lives and livelihoods of 400 million people across northern China remained under direct threat as the environmental crisis worsened. Everything only gets more complicated. Amongst the chaos of dust and failing systems, a teacher named Wang Wenbiao maintained a presence in the heart of the desert. He was neither a billionaire nor a world-renowned scientist, but a man who navigated the dunes daily. 10 kilometers is the distance he traveled by bicycle through the sand just to reach his classroom. One can notice the immense physical toll of such a journey when the wind becomes so violent that it threatens to strip the bicycle bare or bury the rider entirely. At first glance, his persistence was a minor detail, but it marked the start of a transformation that many at the time dismissed as pure madness. The teacher continued his struggle against the elements while the desert stood as an unconquered wall of sand. This phase of the crisis reached its peak, setting the stage for an unconventional solution. 1,200,000 rabbits became the industrial engine for a transformation that most observers considered a physical impossibility. By the late 1980s, the desert environment had become so aggressive that sand literally filled the lungs of those attempting to work the land. Why did Wang Wenbiao decide to stay and force the wasteland to pay him rent instead of fleeing the encroaching dunes? The answer lay in a calculated conversion of dead sand into living soil, a process initiated in 1988 with a combination of personal savings and high-interest loans. At first glance, the task of stabilizing shifting dunes seems simple, but in reality, it required a complete reconfiguration of the local ecosystem. Specific biological tools were selected to act as natural anchors for the terrain. The desert willow was the primary instrument chosen for this massive undertaking, functioning less like a decorative plant and more like a piece of biological machinery. One can notice how these trees operate as organic drills, with roots that do not merely spread horizontally across the surface. Instead, they plunge vertically to depths exceeding 90 meters to intercept deep subterranean water tables. This is just the beginning of the stabilization process. The equipment gradually adapted to the hostile logistics of the moving sand. Planting a tree in a medium that flows like liquid presented a nightmare for the engineering teams. Workers first had to map the vast territory to locate hidden pockets of residual moisture beneath the parched surface. To solve the problem of planting speed, they utilized high-pressure water jets to blast deep holes into the dunes in mere seconds. This allowed the young seedlings to be inserted directly into the moist layers before the sand could collapse. Everything only gets more complicated when the wind is factored into the equation. Thousands of kilometers of specialized fencing were constructed using mesh and reeds to serve as physical barriers. These structures protected the vulnerable saplings from being uprooted by the relentless desert gales. Over a period of 30 years, Wang and his technicians successfully planted more than 200 million individual trees. It is visible how this green wall functions as a massive windbreak, effectively reducing wind velocity by 90%. But this is not the limit of the project. Sterile dust cannot be converted into fertile ground by trees alone. The process is only gaining momentum as it moves from mechanical stabilization to biological enrichment. Wang Wenbiao identified a missing component in this industrial puzzle, a biological motor to accelerate the recovery of the soil. He introduced 1,200,000 Rex rabbits into the newly stabilized zones. Known as white gold within the textile industry, these animals possess fur as soft as velvet, with each pelt commanded a market price of $30. This generated the necessary capital to sustain the project without external aid. But the true industrial value of the Rex rabbit was not found in its fur. 200 to 300 offspring per year are produced by a single biological reproduction machine capable of enduring the most extreme desert chills with minimal water consumption. Why was this specific animal chosen for such a harsh environment? At first glance, the selection seems purely agricultural, but in reality, these creatures serve as the primary engine for a closed-loop ecological cycle designed for total efficiency. The architecture of the system relied on willow trees to provide essential shade and protection from the elements. The process is only gaining momentum. Within these specialized ecological farms, the rabbits consume the willow leaves as their primary food source, while their biological systems perform a critical chemical transformation. One can notice how the desert floor remains void of nutrients, standing as an empty expanse of silicon and heat. But the waste produced by these millions of rabbits is exceptionally rich in nitrogen, phosphorus, and potassium, providing the exact chemical components required to revive the dormant earth. Everything only gets more complicated further on. When this natural fertilizer is deposited across the landscape by millions of animals, the physical properties of the sand undergo a visible transition. it is visible how the texture shifts from a golden, lifeless state to a dark and moist consistency. The camera glides along the ground as the sand transforms into nutrient-dense humus. This is not merely a change in color, but a fundamental restructuring of the desert topsoil. Rabbits do not fully digest the seeds of the various grasses they consume during their daily movements. This technical detail means that as they distribute their waste across the dunes, they are literally planting new vegetation across the territory. A perpetual loop is established where the willow trees sustain the rabbits fortify the soil, and the enriched ground facilitates the growth of even more willows. The process is only gaining momentum. 5 tons of humus per year began to accumulate on every single acre of treated land as a direct result of this biological interaction. It only looks obvious in hindsight, but the speed of the recovery was unprecedented. In a time frame of only 3 to 5 years, what had previously been a sterile, shifting dune was completely converted into stable, arable land. The desert was retreating under the pressure of this biological expansion, but scaling this success to a national level required more than just animal husbandry. Raw energy was the next requirement for the industrial evolution of the project. With the local economy finally stabilized through the consistent sale of rabbit meat and pelts, the focus shifted toward the potential of the sky. 196,000 solar panels form the foundation of the Juma Solar Power Plant, an industrial installation that transcends simple utility. Engineers did not merely arrange these photovoltaic modules in standard rows, but instead meticulously calculated their placement to create a massive industrial portrait. One can notice how the dark blue panels depict a giant galloping horse, a structure so vast in its physical scale that it secured a place in the Guinness World Records. Why was such a complex geometric arrangement chosen for a power facility? While the visual design is striking, the primary objective remains the generation of approximately 1,500,000,000 kilowatt-hours of electricity annually. This massive output provides sufficient electrical power to sustain the households of 200,000 people. It seems simple to focus only on the electrical yield of such a project, but in reality, the most significant technical transformation occurs directly beneath the glass surfaces. In the desert environment, extreme solar radiation serves as a relentless force that accelerates the evaporation of all surface moisture. These vast oceans of silicon and glass create a permanent artificial canopy that blocks the wind and reduces its velocity by exactly 50%. Underneath this technological shadow, the ambient temperature drops significantly, and the rate of water loss from the soil diminishes. At first glance, the desert floor was a barren expanse, but now grass begins to grow independently in the microclimate created by the panels. Everything only gets more complicated as the ecosystem evolves. The vegetation must be strictly managed, as excessively tall grass presents a serious fire hazard to the electrical infrastructure. To solve this, the operators introduced herds of sheep and geese to the site to serve as biological maintenance units. One can notice how these animals graze in the shade, functioning as natural lawn mowers, while the automated glass arrays generate power above them. This symbiotic relationship exists in a region previously known as the Sea of Death. The process is only gaining momentum, having generated $10 billion in revenue over a period of 10 years. But a critical technical question remains. Since the introduction of these animals proved so effective for the project, why did a similar attempt involving rabbits result in a complete disaster? 6,000 kilometers to the south, the history of rabbits in Australia unfolds like a cinematic horror narrative. During the 19th century, settlers introduced exactly 24 rabbits for the purpose of recreational hunting. Without the presence of natural predators or a system of biological control, those initial 24 animals multiplied into more than 1 billion individuals in a span of only 50 years. Why did such a small introduction lead to total ecological collapse? One can notice how the animals consumed every available sprout, destroyed the root systems of trees, and stripped the vast pastures bare of vegetation. This unchecked growth transformed 2/3 of the fertile plains of Australia into desolate desert lands. The Australian government attempted every available countermeasure, including the construction of fences spanning 3,000 kilometers in length. They utilized high-yield explosives and released targeted biological viruses to halt the invasion. Nothing functioned as intended. It only looks obvious that a species would behave the same in any environment, but in reality, the contrast between regions is absolute. Why is the rabbit considered a destructive monster in Australia while acting as a vital hero in China? The answer lies in the application of strict industrial control. In the Australian territory, the situation was defined by the chaos of unmanaged nature. In the Kubuqi Desert, the process was a matter of precise engineering. One can notice that the rabbits in China were never released into the wild to run without supervision. They reside within specialized farms inside a completely closed system. These animals function as biological workers. Every single gram of the food they consume and every gram of the fertilizer they produce is calculated with mathematical accuracy. They represent a single link in an industrial chain meticulously designed by human engineers. China was not merely breeding animals, it was managing a sophisticated artificial ecosystem where the animal serves as a technical tool of precision for the manufacture of fertile soil. The process is only gaining momentum at this stage. Nature, when guided with technical respect and intelligence, responded with physical results that seemed almost impossible. After decades of continuous effort, official reports confirmed a phenomenon that defied previous expectations. The groundwater, functioning as liquid gold hidden in the deep strata, began to rise. Over a period of 20 years, the level of the water table in the Kubuqi subsoil rose by between 1.5 and 2 meters in height. One can notice the immense physical significance of this hydraulic shift. If a grandfather had been required to drill a well in this specific location decades ago, he would have needed to reach twice the depth that a modern technician requires today. The water is returning to the surface, and with the presence of water, biological life has followed. The populations of desert foxes, wild deer, and various migratory birds have increased fourfold when compared to the recorded data from 1990. More than 100 species of native plants, which were previously categorized as extinct in that specific geographical region, have started to reappear in the landscape. Where the camera once recorded only a yellow and dusty horizon, one can now observe expanding green patches and shimmering forests. Everything only gets more complicated as the benefits scale upward. Wildlife now maneuvers between the structures of solar panels that generate renewable energy. This project did not simply halt the expansion of the desert, it effectively reversed the passage of time. The ecosystem now sequesters 1,850,000 tons of carbon dioxide from the atmosphere annually. This journey began with a terrifying statistic regarding the planet turning into dust, but the technical history of Kubuqi provides a powerful objective lesson. A professor, utilizing willow trees, glass solar panels, and 1 million rabbits, proved that there are no deadlands. The material is ready to move to the next processing phase without haste. Thus ends one of the key stages of restoration. Billions of dollars have been generated by the transformation of a barren landscape into a thriving green industry. One can notice how the relentless sun, once a source of thermal degradation, has been converted into a sustainable energy reservoir for the coming decades. Why did engineers pursue such a radical shift in a sterile desert environment? It seems simple to view land as either productive or wasted, but in reality, industrial power lies in the ability to solve seemingly impossible problems through calculated engineering. This transition from a plague of heat to a profitable technological oasis marks the beginning of a new era. But this is just the beginning. The horizon of the Baltic Sea is currently occupied by a massive armada consisting of 70 specialized vessels. They are not engaged in a military conflict, yet they are systematically tearing into the seabed to facilitate an investment of 10 billion euros. The primary objective is the construction of the longest submerged link in the entire world, connecting Germany and Denmark. It is visible how the fleet operates in unison to execute this massive logistical undertaking. Everything only gets more complicated when considering the scale of the structural components. 100,000 tons is the approximate weight of the individual concrete blocks that engineers must sink to the ocean floor. This mass exceeds that of a standard cruise ship, yet the technical requirements demand a placement precision measured in mere millimeters. At first glance, such accuracy seems unattainable in the total darkness of the deep ocean. But in reality, this is the most extreme infrastructure project currently underway in Europe, requiring constant monitoring of hydraulic pressures and seabed stability. The process is only gaining momentum. To comprehend the sheer scale of the engineering required, a study of the geographical constraints is mandatory. On one side lies the German island of Fehmarn, while on the opposite side sits Lolland, the fourth largest island in the Danish territory. A single stretch of treacherous water separates these 2 points. The only current method of passage is a ferry service that functions as a persistent logistical bottleneck. 45 minutes is the minimum amount of time lost during a single crossing, even under optimal conditions. One can notice how vehicles must wait for arrival and boarding, a process that consumes hours of productive time daily. It only looks obvious that the ferry is a reliable link, but in reality, the Baltic storms frequently bring the entire transport of goods between Scandinavia and Central Europe to a complete standstill. This causes the supply chain to freeze for unpredictable durations. It gets more complex further on. Engineers and government officials have debated a permanent solution since the decade of the 1990s. The most obvious answer was the construction of a bridge spanning 12 miles of open water. This original plan detailed a massive structure composed of steel and reinforced concrete. Transition to the next level. Imagine 4 massive pillars rising from the waves to support a bridge deck designed to withstand the violent winds of the Northern Sea. Therefore, every design choice was dictated by the need for structural longevity against the corrosive maritime environment. 919 feet of height is the staggering elevation the original bridge design reached, surpassing the stature of numerous world-renowned skyscrapers. Why was such a colossal structure necessary for the Fehmarn Belt? The bridge required these extreme dimensions to allow massive ocean-going vessels to navigate underneath, necessitating spans of a length never before attempted in the annals of engineering history. But this ambition forced a confrontation with physical reality. Engineers scrutinized the environmental risks and ultimately retreated from the aerial plan. In 2010, the responsible entity, Fehmarn AS, issued a startling public declaration regarding the project. Building a bridge of that scale would have pushed human technological capabilities to the absolute breaking point. The probability of a structural catastrophe was deemed unacceptably high. The bridge was officially categorized as an over-engineered and excessively complicated solution. At first glance, the alternative might seem more difficult, but the decision was made to move beneath the seabed. A tunnel would require an investment of €5.5 billion, nearly identical to the projected cost of the bridge, yet it would systematically eliminate the hazards posed by gale-force winds and maritime storms. One can notice how the strategic focus shifted toward piercing the darkness of the Baltic floor. The revised engineering blueprint called for the creation of an 11-mile tunnel, ranking it among the largest man-made structures ever conceived by the human race. It gets more complex further on. How does one construct a tunnel in the middle of a vast sea when standard logistics dictate that materials cannot simply be delivered by a fleet of trucks? The sheer scale of this undertaking meant that traditional supply chain methods would suffer a total collapse under the weight of the requirements. The solution devised by the planners was every bit as radical as the tunnel itself. If a facility capable of such output does not exist, then a bespoke factory must be fabricated on site. Preliminary work commenced in 2019 with a singular, unwavering objective. This was the monumental task of erecting a temporary industrial city. In Rødbyhavn, Denmark, a massive production plant was born, sprawling across approximately 11 million square feet of terrain. One can notice the immense footprint of this facility, which currently stands as the largest dedicated tunnel production factory on the planet. Inside this industrial giant, 6 distinct production lines were assembled to operate continuously through the day and night. The process is only gaining momentum. A factory of this magnitude requires a constant influx of raw materials and energy to remain functional. Consequently, Fehmarn AS undertook the construction of an entire deep-water port from the ground up. This port does not cater to tourists or commercial transit. The equipment gradually fills the docks, as the harbor was designed specifically for the arrival of heavy, specialized components. One can notice the heavy lifting cranes and massive berths designed for industrial barges. The harbor functions as the primary artery for the entire construction site. The port serves as the logistical heart, ensuring that the colossal volume of concrete and steel reaches the production lines without delay. From here, the transition to the assembly of the tunnel segments begins with mathematical precision. 80,000 tons of material arrive by sea every single week, including massive quantities of rock, sand, gravel, and steel. Why is such a colossal maritime logistics chain necessary for this project? Moving this volume of cargo by road would require a literal army of heavy trucks that would paralyze the entire European highway network. The ocean serves as the only viable artery for a supply chain of this magnitude. Around the manufacturing site, residential quarters and administrative offices rose from the ground to form a dedicated community. This entire infrastructure exists for a single purpose: to feed the industrial beast designed to link two nations together. What emerges from this facility defies standard engineering imagination. The tunnel is not excavated through the earth, like a traditional subway system, but is instead assembled like a giant set of building blocks. One can notice how the components resemble a massive Lego set, yet these pieces are the heaviest concrete objects humanity has ever attempted to transport. Each individual tunnel section extends to a length of 712 feet. To visualize this scale, one must imagine two full-sized football fields placed end-to-end. The width reaches 131 feet, while the height stands at 33 feet. This creates the footprint of a three-story building lying on its side. But this is just the beginning. The number that truly creates a sense of scale is the total weight. Each of these massive sections weighs 73,500 tons. To put this into a technical perspective, consider a modern cruise ship like the MS Zuiderdam, which accommodates 2,000 passengers and weighs 82,000 tons. It is visible how each tunnel segment produced here weighs nearly as much as an entire cruise liner. The project does not require merely one or two of these units. Engineers must manufacture 79 of these titanic sections. This represents an entire fleet of stone vessels that will never float on the surface, yet must be moved, transported, and submerged with surgical precision. At first glance, the location of the plant might seem arbitrary, but in reality, the factory had to be positioned directly on the coastline. Moving these concrete monsters across land would be physically impossible due to their sheer mass and dimensions. While the factory rouge on the shore, a parallel operation of planetary surgery is underway at sea. During the peak of activity, the Fehmarn Strait witnessed a concentration of 70 heavy vessels working simultaneously in a coordinated dance. Their mission was simple in concept, but brutal in execution. They had to carve a deep trench into the seabed to house the tunnel sections. It gets more complex further on. The engineers could not simply rest the tunnel structure on the ocean floor. The equipment gradually removed layers of earth so the tunnel could be buried and protected from massive ship anchors and powerful underwater currents. Dredgers worked day and night without interruption, systematically removing the seabed along a stretch of 11 miles. The camera glides along the excavated path where the soil is meticulously cleared. The process is only gaining momentum as the underwater landscape is permanently altered. The material leaves the excavation site, transitioning into a calm stage of preparation for the next phase. 164 feet is the total width of the underwater trench, carved through layers of shifting silt and rock-hard limestone. Why did the dredging fleet require constant mechanical upgrades throughout the operation? It would seem that standard maritime equipment could handle the seabed, but the alternating density of the geology would have shattered the cutter heads without these reinforcements. As a result, the engineering team successfully hollowed out a massive corridor, reaching depths of 49 feet below the ocean floor. 76 million cubic feet of soil and rock were extracted from this artificial abyss during the excavation process. One can notice how the disposal of such an incomprehensible volume of debris transformed from a logistical burden into a geographical expansion. It seems simple to merely dump the waste further out at sea, but in reality, the engineers calculated a method to utilize the material for land reclamation. The soil was meticulously transported to the coastline to facilitate the creation of 741 acres of entirely new solid ground. Where the ocean surface once stood alone, there are now functional beaches and expanded natural zones, effectively turning excavation waste into a coastal asset. But this is just the beginning. 10 billion euros represent the staggering financial stakes that could vanish in a single moment during the immersion phase. With the trench fully prepared and the massive concrete structures emerging from the factory, the project enters its period of maximum technical tension. The process of sinking these segments is scheduled to commence in the year 2025. To maneuver these blocks, which weigh 73,000 tons each, specialized submersible pontoons are deployed to securely grip the concrete sections. The process is only gaining momentum. A fleet of heavy tugboats pulls the concrete monsters slowly toward the open sea, navigating them until they are positioned with absolute precision over the dark trench. One can notice that the descent into the depths is far from an automated procedure. Inside a dedicated control room located directly on the pontoons, an elite team of 22 specialists monitors every centimeter of the downward trajectory. They manage complex winching systems equipped with steel cables that reach a total length of more than 124 miles. It gets more complex further on. Ballast tanks are gradually filled with seawater to overcome the physical buoyancy of the air trapped inside the hollow tunnel segments. It looks outwardly simple to sink an object, but in reality, the engineers must fight against the laws of physics to force the concrete down. The ultimate challenge remains the precision of the final alignment at the bottom. In the absolute darkness at a depth of 40 meters, the team must fit one massive block into the next with surgical accuracy. 1/2 of an inch. That is the exact margin of error allowed for the placement of the massive tunnel segments. Why is such surgical precision required at the bottom of the ocean? If the alignment deviates by even a fraction more, the structural ceiling fails immediately, and water begins to inundate the entire interior. Underwater cameras and specialized sonar arrays guide every centimeter of the descent. One can notice how the equipment moves with deliberate slowness through the dark currents. When the concrete faces finally make contact, giant rubber gaskets seal the union between the two sections. Engineers designed these rubber components to withstand the crushing pressure of the sea for 120 years without degradation. The entire process is a test of human endurance. Transporting and installing a single individual session constitutes a marathon of 40 hours of uninterrupted tension for the entire crew. Once the connection is verified, the tunnel is buried under layers of sand and protective stone, causing the structure to disappear forever from human sight. But a project of this immense magnitude does not occur without leaving deep scars on the environment. The initiative faced the combined fury of natural elements and organized environmentalists. It is visible how the seafloor was not a barren desert, but a space teeming with complex biological life. Ancient reefs lay directly in the path of the heavy dredging machines. At first glance, the initial project documents stated that these reefs would remain safe from harm, but in reality, the truth emerged in the year 2020. Vital habitats faced total destruction from the construction footprint. The court eventually halted the work temporarily to review the ecological impact. However, the machine of industrial progress cannot be restrained for a long duration. The legal restrictions were eventually lifted, effectively condemning 23 acres of natural reefs to disappear. The process is only gaining momentum. As a form of ecological compensation, the company Femern AS pledged to construct 105 acres of new artificial reefs. This is an attempt to settle the environmental debt owed to the ocean. And it is not only nature that suffers during such a transition, as human fear also plays a significant role. The ferry system currently operates 315 voyages every week and serves as the primary livelihood for many local families. When the tunnel finally opens, those ferries and the jobs they support may vanish entirely. There is also a structural problem that no one predicted at the start of the project. The old Fehmarn Sound Bridge stands as a technical relic from the year 1958. Built during the height of the Cold War, this bridge contains secret chambers hidden within its massive pillars. These voids were designed to hold explosive charges to destroy the bridge in the event of an enemy invasion. The problem remains that this aging structure is the primary gateway into Germany, and it is physically falling apart. Load tests demonstrated that the old bridge could never support the heavy volume of traffic the new giant tunnel will produce. It only looks obvious that a bottleneck would form here. Constructing a younger sibling for the bridge became the only viable solution to avoid a logistical disaster. This requires adding even more capital to the total project budget. A second, smaller tunnel with a length of approximately 1.5 kilometers will be built to replace the functions of the old bridge. This secondary structure will utilize the exact same factory and the same immersion technology as the primary giant tunnel. The material is ready to move to the next processing phase without haste. 114 million euros is the cost of a single specific project within this massive engineering undertaking. Why is it necessary to invest a total of 10 billion euros and move literal mountains of earth? At first glance, the scale of the investment seems disproportionate to the geography, but in reality, the entire project is designed to solve the critical issues of speed and international connectivity. After decades of complex planning and multiple delays that pushed the completion date from 2021 to 2029, the end of the construction phase is finally visible on the horizon. The logistics of the region are currently dictated by the sea. Today, the crossing from Puttgarden to Rodby is a 45-minute journey by ferry, which does not include the additional time required for boarding and waiting at the terminal. Once the tunnel opens to traffic, vehicles will enter the structure and reach the opposite shore in only 10 minutes. One can notice how the removal of maritime waiting times transforms the crossing into a seamless transit. The process is only gaining momentum. For rail transport, the technical transformation is even more significant. New high-speed trains will accelerate through the tunnel at 124 miles per hour. This allows the crossing of the strait to be completed in just 7 minutes. 7 minutes is all that will be required to traverse the expanse of the sea. The camera glides along the planned tracks where the impact on regional geography becomes immense. Traveling between Copenhagen and Hamburg, the two largest metropoles in the area, currently requires nearly 5 hours of transit time. With the tunnel in operation, this duration drops to 2 hours and 30 minutes. Denmark and Germany will cease to function as distant neighbors and instead integrate into a unified high-speed economic corridor. It is visible how the shortened travel times foster a massive community of people moving between these hubs daily. Everything only gets more complicated as the final logistics are integrated. The integration of these two regions creates a dense network of social and economic exchange that previously relied on slow ferry routes. From here, the transformation moves to the next phase of processing as the final sections of the tunnel are prepared for installation. The material is ready to move to the next processing phase without haste. 10 billion euros is the price of the ambition required to rewrite the geography of a continent. Why would engineers plunge massive concrete structures into the maritime abyss to create the Fehmarn Belt Tunnel? This engineering monument serves a single purpose: to reclaim 2 hours of time by refusing to accept the natural boundaries of the sea. Time remains the most precious industrial resource, and this 10 billion euro investment represents a physical defiance of distance. But the scale of human ingenuity is not limited to titanic tunnels. 60 lamps are produced every single second across the globe. This represents a total output exceeding 2 billion units manufactured every year. One can notice how a silent revolution has shifted from massive infrastructure into the very center of the modern home. It seems simple at first glance, but this transition saves the planet over $200 billion in electricity costs annually. How did the transition from a fragile metal filament trapped in burning glass to a microscopic semiconductor occur? A single grain of rice is larger than the silicon chip that now dictates the future of illumination. What is the industrial secret that allows one lamp to expire after 1,200 hours, while the other operates for tens of thousands? The process is only gaining momentum. Two distinct eras of technology are now colliding in a struggle for efficiency. The age of fire stands against the age of silicon. The journey of the classic incandescent lamp begins not with the assembly of metal components, but with the fusion of glass and heat. Transparent glass tubes, shaped with geometric perfection, move along a rotating conveyor belt at a constant speed. One can notice how these tubes serve as the primary blocks for the outer casing. Each glass segment is gripped firmly between two mechanical heads before it plunges into a concentrated bath of intense flames. The process gets more complex further on. Gas nozzles positioned in a circular array release thermal energy until the environment reaches 2,300 degrees Fahrenheit. It is visible how the glass becomes soft and flexible, losing its rigidity and moving with the viscosity of honey. As the tube maintains a steady rotation, the mechanical forces cause the edge to expand outward in a precise flare. This thermal molding prepares the glass for the next stage of structural integration. The molten material continues its path through the automated line without haste. Thus, the glass reaches the standard required for the further stage of production. 200 milligrams of tungsten and a precise sequence of glass manipulation form the foundation of the lamp base. Why is a tiny glass exhaust tube inserted directly into the center of the neck? This step only looks obvious, but it is the most critical part of the entire design. This small canal serves as the primary gateway for creating a vacuum, and without it, the bulb would fail instantly. At the same moment, two thin copper wires are positioned on opposite sides to function as electrical conductors. Automated robotic arms intervene with incredible precision the exact second the glass reaches a state of high malleability. These manipulators ensure that the internal components are centered within a fraction of an inch. But this is just the beginning. The entire assembly moves through a series of specialized burners, emitting even more intense heat. One can notice how the glass begins to soften and flow, sealing itself hermetically around the metal conductors to prevent any air leakage. The process is only gaining momentum. A separate station utilizes mechanical fingers to gently bend the copper wires into two small hooks that curve inward toward the center. These hooks are not decorative, as they function as the structural supports that will soon cradle the glowing heart of the lamp. It is visible how the equipment monitors every neck with optical sensors to maintain strict dimensional tolerances. Why is tungsten the only material chosen for the coil? The production process now transitions to the most delicate phase, where the filament, the true soul of the lamp, is installed. Tungsten is an extraordinary metal capable of withstanding more than 4,000 degrees Fahrenheit without disintegrating or melting. The machine slowly unwinds a coil of tungsten wire to prepare it for shaping. This wire is pulled and wound into microscopic springs that are only slightly thicker than a single strand of human hair. Precision magnetic tweezers controlled by an automated arm perform the delicate operation of picking up a spring and attaching both ends to the copper hooks. Everything only gets more complicated. Once the filament is secured, high-speed sensors verify that the tungsten coil is under the exact required tension. If the wire is too loose, it will vibrate and fracture during operation, and if it is too tight, the thermal expansion will cause it to snap immediately. One can notice a thin layer of zirconium solution being applied to the entire wire assembly before the final sealing occurs. This invisible protective film acts as a specialized barrier to prevent moisture damage and slow down the process of oxidation. This ensures the filament maintains its integrity while operating within the future environment of inert gas. The internal structure is now fully reinforced and verified. The heart of the device is locked in its correct position, and the equipment prepares for the final stage of closing the outer shell. Thus, the transformation moves to the next phase of processing. 1,600 degrees Fahrenheit is the temperature at which the precision fusion of the glass components begins. Why must the rotating gripper and the circular glass casing be positioned with such absolute alignment on opposite sides of the assembly line? At first glance, the placement seems simple, but in reality, any deviation would prevent the formation of a structurally sound vacuum seal. Robotic arms rotate both the transparent lamp body and the casing in opposing directions, meticulously guiding the seam through a concentrated sequence of high-velocity gas flames. The process is only gaining momentum. One can notice how the intense heat acts upon the material in a matter of seconds, causing the glass to soften until the two distinct pieces fuse into a single seamless bond. The resulting connection is so uniform that the transition point becomes nearly invisible to the naked eye. Immediately following this fusion, the lamp enters a specialized zone where forced air cooling is applied to the structure. This stream of cold gas serves a critical technical purpose, as it instantly stabilizes the temperature to prevent the molten glass from deforming under its own weight. Hundreds of lamps advance along the conveyor in a state of near completion, yet they remain open to the atmosphere. The process moves to the next level as the assembly enters one of the most vital phases for ensuring long-term operational durability. This stage involves the total evacuation of internal air and the subsequent injection of a specialized inert gas mixture. A vacuum pump head, equipped with a heavy-duty rubber gasket, receives each individual lamp to begin the extraction. The primary objective is the total elimination of oxygen, which acts as a destructive agent against the tungsten filament. If even a trace of oxygen remains, the tungsten would ignite and vanish in a fraction of a second once the lamp is powered. it gets more complex further on. The equipment gradually connects the thin exhaust tube located at the neck of the bulb directly to the high-pressure suction system. Over a period of 10 to 12 seconds, the mechanical pumps pull the internal environment toward a near-perfect vacuum. This precise duration is calculated to remove not only the air, but every residual molecule of moisture that might compromise the internal chemistry. One can notice the steady movement of the carousels as they cycle through these evacuation stations with rhythmic precision. Everything only gets more complicated as the final sealing begins. It only looks obvious that the vacuum alone is sufficient, but in reality, the lamp requires an internal buffer to function. Immediately after the vacuum threshold is reached, an automated injector releases a strictly measured dose of argon mixed with nitrogen into the bulb. Because this gas mixture is chemically inert, it does not react with the white-hot filament during operation. The gas acts as a physical barrier, effectively slowing the evaporation of the tungsten atoms and preventing the accumulation of dark residues on the inner surface of the glass. The internal atmosphere is now stabilized, allowing the production line to transition into the final finishing stages. 1,800 degrees Fahrenheit is the temperature reached by the gas torch as it focuses its flame onto the exhaust tube tip. Why is such intense thermal energy directed at this specific point of the glass structure? The heat causes the material to liquefy and fuse, creating a hermetic seal that permanently traps the inert gas inside the bulb. But this is just the beginning. The lamp is now sealed, yet it remains isolated from any external power source. An automated robotic arm moves with calculated speed to install the pre-molded aluminum base onto the glass neck. One can notice how two slender lead wires extending from the interior are positioned for the final electrical connection. One lead passes directly through the central aperture of the base, where it is secured by a precision heat weld that hardens instantly. The second wire is routed to the side of the aluminum shell and soldered to complete the electrical circuit path. It only looks obvious to move to packaging now, but every unit must first survive the most rigorous evaluation of its tungsten filament. Hundreds of lamps are secured into specialized test sockets as they travel along the automated conveyor system. These supports engage with a power source, initiating a rapid cycle of activation and deactivation that lasts for exactly 90 seconds per wave. This process simulates real-world operating conditions, subjecting the delicate tungsten to intense mechanical and thermal stress. During this sequence, the electrical current rises gradually from 50% to 120% of the nominal voltage rating. If the internal filament fails to withstand the surging load, the bulb burns out immediately and a manipulator removes the defective unit from the production line. One can notice the warm golden glow as the final incandescent lamps exit the assembly area. At first glance, this radiance appears as a mechanical tribute to over 100 years of industrial history. However, inside modern manufacturing facilities, a new generation has already superseded this technology in the form of the light-emitting diode, or LED. The process is only gaining momentum. The manufacturing protocol for these modern light sources could not be more different from their glass predecessors. LEDs do not require a vacuum environment or a specific blend of inert gases to function. Instead, the primary engineering requirement is exceptional heat dissipation to safeguard the microscopic light-emitting chip located at the core. This is why the fabrication sequence begins with solid bars of aluminum. The camera glides along the heavy machinery as these metal bars are fed into high-pressure die-casting units to form the structural housing. This process shapes the body of the lamp, including the characteristic cooling fins designed for thermal management. These aluminum casings are subsequently drilled and polished by automated tools to create perfectly smooth contact surfaces. Such precision ensures that heat transfers efficiently from the LED chip to the external atmosphere. The material is ready to move to the next processing phase without haste. 500 degrees Fahrenheit is the intense thermal threshold reached within the heating chamber to initiate the transformation of raw materials. Why is such a high temperature necessary for the production of a simple plastic dome? At first glance, the process looks like basic melting, but in reality, the polycarbonate must reach a specific viscosity to ensure total optical clarity. The transition to the next level begins when thousands of tiny transparent plastic granules are poured into a hopper, feeding the system continuously. The liquid material is injected into precision molds in a matter of seconds. one can notice how the injection pressure is maintained at precisely 2,000 pounds per square inch to force the molten polycarbonate into every corner of the die. This extreme force ensures that the plastic fills all contours perfectly without trapping a single microscopic air bubble. It is visible how the hydraulic press holds the mold shut against the internal pressure of the melt. The process is only gaining momentum as the shape of the diffuser begins to solidify. Everything only gets more complicated as the cooling phase starts. For the next 20 to 30 seconds, a forced cooling system actively stabilizes the molecular structure of the dome. This rapid thermal reduction is vital because it preserves the crystalline clarity of the polycarbonate and prevents any warping. The equipment gradually releases the finished dome, which will eventually serve to soften and spread the light from the diodes. Hundreds of round white circuit boards move firmly along a conveyor belt in a separate assembly zone. Each unit is prepared to receive the seeds of light that will define its function. It only looks obvious to place components on a board, but in reality, the preparation of the surface is a delicate mechanical operation. A precise layer of solder paste is printed onto the surface of each board with jewelry-like accuracy. This metallic paste acts as a temporary adhesive, ensuring that the light-emitting diode chips remain in their exact positions during high-speed movement. The surface mount technology machine begins its rapid operation mere moments after the paste is applied. The robotic arm of the SMT system picks up dozens of chips every single second with a hiss of pneumatic suction. These components are smaller than a single grain of rice, yet the machine places them exactly on their designated contact points without a millimeter of deviation. One can notice the blur of the manipulator as it populates the boards at a speed that exceeds human capability. This stage concludes the preparation of the electronic core, leaving the boards ready for the final bonding process. 0.002 inches is the maximum margin of error allowed for the placement of these microscopic components. Why is such extreme accuracy necessary when dealing with simple lighting? While the process only looks obvious, any deviation of more than a few thousandths of an inch would prevent the electrical contacts from aligning, leading to a complete failure of the circuit board. One can notice how the surface mount machines position each chip with mechanical speed and absolute stillness. But this is just the beginning. The equipment moves the populated boards into a high-temperature reflow oven. Controlled thermal energy gradually melts the solder paste to fuse the chips to the circuitry. This creates permanent and stable electronic connections capable of withstanding years of thermal cycles. The camera glides along the exit of the oven where the boards emerge, glowing with dozens of tiny, perfectly aligned points of light that reflect off the metallic traces. These units are now structurally ready to be integrated into the main heat sink housing. Technicians take over at the manual assembly stations once the circuit boards are finalized. Individual skill remains the primary factor in this specific phase of production. The technicians carefully install the driver, which functions as the power converter for the entire system. Because LEDs are sensitive to electrical changes, this component allows the unit to operate with total stability, even when the input voltage fluctuates. It is visible how the technician uses a precision soldering iron to connect the power wires between the LED board and the driver. Every joint must remain bright and perfectly clean to ensure long-term conductivity. The driver is then lowered into the internal cavity of the lamp body and secured in its permanent position. Everything only gets more complicated as the assembly reaches the final structural components. The familiar Edison screw base, known technically as the E26 cap, is the last electrical piece to be added. The driver wires are attached to the base using a rapid and strictly controlled soldering strike before the entire assembly is energized for an instant functional test. One can notice the immediate flash of light as the circuit completes for the first time. The process is only gaining momentum as the lamp enters its final physical transformation, involving the diffuser cover and the total inspection protocol. Robotic arms equipped with vacuum grippers pick up transparent polycarbonate domes and place them precisely over each lamp structure. A thin, uniform ring of heat-resistant silicone is applied along the circular edge by an automated nozzle. The robotic arm then exerts a specific amount of downward pressure to seat the dome against the aluminum frame. This creates a hermetic seal that blocks the entry of moisture and microscopic dust particles. Curing takes only a few seconds before the lamps transition to the optical testing conveyor. Integrated optical sensors measure the exact lumens, the diffusion pattern, the color temperature, and the flicker-free stability of the emission. If the light spreads with perfect uniformity and without any scintillation, the lamp is cleared to move to the automated packaging zone. Robotic systems place the finished units into anti-static trays to prevent any electrical discharge during transport. Protective sleeves are wrapped around each bulb while printers apply QR codes and specific production batch numbers to the exterior. The equipment gradually fills the shipping containers, marking the end of a highly synchronized manufacturing cycle. But this journey of industrial transformation took more than 100 years to reach this level of efficiency. The story began in 1879. Thus ends one of the key stages of LED lamp production. 40 hours was the exact duration of the continuous glow emitted by the very first functional incandescent light bulb. Why did this brief interval of light mark a fundamental shift in human history? The initial glow proved that electricity could be tamed for illumination, but the fragility of the early carbonized bamboo filaments meant the technology was not yet practical for the masses. Only 12 months later, the design underwent a rigorous refinement process that extended the operational lifespan to more than 1,200 hours, effectively launching the era of widespread electric lighting. But this is just the beginning. It only looks obvious that a glowing wire is an ideal solution, but in reality, the inherent physics of the incandescent bulb revealed severe technical limitations over the following decades. One can notice how the glass housing becomes hot to the touch because the vacuum-sealed environment fails to prevent massive thermal energy loss. High energy consumption and extremely low luminous efficiency characterize the tungsten filament, which eventually paved the way for a radical technological shift at the dawn of the 21st century. Everything only gets more complicated. The emergence of light-emitting diode technology replaced the physical filament with solid-state semiconductor circuits. $200 billion is the estimated global savings generated by this transition, a figure that matches the total annual energy output of hundreds of thermal power plants. The equipment gradually moved away from fragile glass tubes toward LED chips that are now smaller than individual grains of sand. Transition to the next level. One can notice how human engineering has successfully transformed raw energy into light and technology into physical endurance. While the original incandescent bulb provided the first artificial glow, modern LEDs carry this legacy forward with unmatched performance and operational lives that span tens of thousands of hours. It seems simple to replace a bulb, but in reality, the mission to illuminate the world has evolved into a quest for smarter and more sustainable systems. The process is only gaining momentum. Computers are updated every 2 or perhaps 5 years, while mobile phones and vehicles are discarded at an even faster rate. Every machine left behind and every fragment of metal considered waste contains dozens of precious elements. These are not common materials found on the surface. They were originally extracted from deep within the earth through an immense expenditure of labor, energy, and mechanical engineering. The camera glides along the piles of discarded shells. $700 billion is the valuation of the global industry that begins at the moment a machine is declared useless. Within colossal industrial facilities, these metals do not reach an end, but rather undergo a process of rebirth. What appears to the eye as a disorganized scrap graveyard is actually a nursery for the resources of the future. At first glance, a mountain of twisted steel and mixed plastic seems impossible to sort, but in reality, it is a calculated puzzle of logistics. How does the industry untie this knot of copper wires and composite materials? To transform this chaos back into metal, as pure and strong as the day it was mined, the system utilizes temperatures of thousands of degrees. This represents one of the most incredible physical transformations on the planet, beginning at a specialized metal collection yard. From here, the transformation moves to the next phase of processing. 400 million tons of iron ore remain undisturbed within the earth every single year because of this global network. Why is this urban mining operation considered more strategic than traditional extraction? It only looks obvious that discarded metal is waste, but in reality, these collection and storage sites function as high-tech reservoirs of raw material. This massive preservation of natural resources translates into a direct economic saving of hundreds of billions of dollars by eliminating the immense costs associated with deep earth mining, transoceanic transport of raw ore, and complex waste treatment. One can notice how the process begins with extreme precision at the weigh station. Giant trucks, carrying the discarded structural remains of modern society, must first navigate onto electronic scales capable of measuring 60 tons. Every single kilogram of incoming material is logged into a digital database with absolute accuracy. In the most advanced processing centers, radio frequency identification technology, or RFID, is utilized to track each specific shipment. This level of oversight is not an exaggeration. It is a critical technical requirement to prevent the accidental loss of immensely valuable non-ferrous metals like copper, aluminum, or nickel, which could otherwise be vanished within the high-volume flow of steel. But this is just the beginning. The strategic objective of these massive facilities is inherently global in its scale. Highly industrialized nations such as Japan, Germany, and South Korea integrate these centers as vital links within the international trade of recycled commodities. Between 30 and 40% of the entire global flow of recycled metal is currently transported across the world's oceans. Tens of millions of tons of steel scrap are exported from the United States to provide the necessary feedstock for the heavy steel mills located in India, Turkey, and Vietnam. The environmental consequence of this logistical chain is significant. Each individual ton of scrap that is successfully collected prevents the release of more than 2 tons of carbon dioxide into the atmosphere. This initial stage of the cycle serves as the primary line of defense for a sustainable economy. It seems simple to move piles of metal, but in reality, this chaotic and voluminous material represents a logistical nightmare for engineers. The jagged, irregular shapes make the scrap inherently dangerous to handle and inefficient to transport in its raw state. Before the material can be safely moved or refined, its physical form must be systematically tamed through mechanical intervention. The process is only gaining momentum. This is the point where the application of raw hydraulic force becomes a technical necessity. One can notice how the camera glides along as massive hydraulic claws descend upon the piles. Deconstructed car chassis, heavy industrial machine frames, and mangled sheets of structural metal are gripped by the steel teeth of the manipulators. The equipment gradually maneuvers these awkward loads toward the next phase of the transformation. Everything only gets more complicated as the metal is prepared for its transition from discarded debris into a standardized industrial resource. The heavy machinery continues its work, ensuring the material is ready for the intense processing that follows. 3,000 pounds per square inch is the relentless pressure generated by modern compaction systems in a demonstration of pure mechanical power. Why is such immense force applied to loose scrap? It might seem that simple piling would suffice for transport, but without this calculated compression, the metal remains a chaotic mass of unstable voids that pose a direct threat to the entire facility. The process is only gaining momentum. Hydraulic rams drive forward with a slow, steady hiss, crushing hundreds of kilograms of metal in a matter of minutes. One can notice how the twisted frames and jagged sheets collapse into a single, dense and solid block. These resulting bales typically measure between 20 and 40 inches on each side. This precise geometry serves a dual purpose, as it maximizes every available square inch of space within shipping containers or transport trucks. At first glance, this is a matter of logistics, but in reality, the primary driver is absolute safety. The stakes in this environment are exceptionally high. Total compression eliminates treacherous empty spaces within the scrap pile that could harbor flammable gases or hazardous oil residues. Most dangerous of all are the defective lithium batteries that often hide within the debris. Everything only gets more complicated further on. A single forgotten battery can trigger a devastating fire or explosion during transit if it is crushed incorrectly or allowed to shift. This critical step ensures that what was once a volatile and chaotic heap transforms into a compact, manageable block of metal. The larger structural pieces are now contained, but millions of complex mixed components remain to be processed. One can notice the arrival of engines, computers, household appliances, and thick bundles of wiring. These items represent a physical union of dozens of different materials bonded together. To separate these elements, simple pressure is no longer sufficient. It requires the total destruction of the structural integrity of the objects. The process transitions to the next level. The materials are fed directly into the shredder, which serves as the pulsating heart of the recycling line. Inside the heavy crushing chamber, massive steel hammers spin at dizzying speeds ranging from 500 to 2,000 rotations per minute. They strike the scrap repeatedly with a sound that is practically ensurdecita. The sheer force tears the metal into tiny fragments measuring only a few centimeters or even millimeters in length. Efficiency at this stage is remarkable. A single shredding system can process between 5 and 100 tons of scrap every hour, depending on its specific engineering design. But the objective of this controlled violence is not merely a reduction in size. The goal is to break the physical bonds that hold different elements together. It gets more complex further on. This incredible mechanical force is what finally liberates the valuable materials trapped inside the assemblies. One can notice how the copper wires are stripped clean of their plastic insulation during the impact. The heavy hammers crack the steel cores inside motors and release the copper and tin from integrated circuit boards. What was once a functioning motor is now reduced to a pile of its fundamental base components. Now that the materials are physically free from one another, the true engineering begins to take shape. The mixed stream of fragments moves along a conveyor belt at a steady speed. How can the system distinguish between steel, aluminum, copper, and plastic in such a fragmented state? The first stage of separation relies on the application of brute magnetic force. A high-power magnet, usually configured as a heavy rotating drum, is suspended directly over the moving belt. It generates an intense and constant magnetic field. Immediately, every ferrous piece, including fragments of iron and steel, is snatched from the flow. It is visible how they are literally pulled upward against the force of gravity and diverted into a dedicated separate container. The remaining materials continue their journey along the line. These consist of non-ferrous metals, such as aluminum and copper, alongside non-metallic substances like plastic and rubber. The materials move toward the next phase of sorting without delay. 100% of the technical sensors and automated scanners have their limits and cannot identify every single anomaly. Why is the most precise filter of all, the human worker, still integrated into this high-tech chain? Automated systems operate on rigid algorithms that can be deceived by complex shapes or layered materials. This is where the stakes rise once again, as the scrap moves under intense, high-output lighting for the final stage of manual verification. Workers operate in dedicated lines where their trained eyes and rapid hand movements perform tasks that no digital sensor can execute with such high levels of adaptability. They search for specific contaminants that have the potential to compromise the entire fusion process in the furnace. It only looks obvious to the untrained observer, but in reality, a single piece of mixed metal alloy could contaminate an entire batch of high-purity material. One can notice how the staff identify a damaged battery that managed to bypass the magnetic separators. They extract electronic parts or components contaminated with heavy grease before the material moves further. A single oversight at this junction can result in losses exceeding tens of thousands of dollars and ruin dozens of tons of pure metal. This human filtration layer serves as the ultimate guarantee that only the cleanest raw material proceeds to the melting stage. But this is just the beginning. The scrap metal is now thoroughly cleaned and categorized by its specific chemical type after passing through this rigorous double verification system. Everything only gets more complicated as the material faces the fire for its technical rebirth. Depending on the physical properties of the scrap, it is directed to different specialized furnaces. Steel and cast iron are sent into electric arc furnaces that utilize high-voltage currents. Aluminum, copper, and zinc are diverted to induction furnaces. Within these industrial giants, temperatures reach nearly unimaginable levels of 2,500 degrees Fahrenheit, which is approximately 1,370 degrees Celsius. It is visible how this immense thermal energy transforms solid metal into a uniform lake of glowing liquid. However, this stage is not merely about melting, but about refining the structural integrity of the substance. Inside the furnace, the molten metal is subjected to constant agitation to ensure the chemical composition remains perfectly homogeneous throughout the volume. At first glance, the melt seems ready, but in reality, lighter impurities known as slag must be managed. One can notice how this layer of waste floats to the surface like a thick crust. These impurities are then removed either by automated robotic arms or manually by workers wearing specialized heat-resistant suits. To calibrate the final characteristics of the product, operators introduce refining agents such as silicon or manganese. The process is only gaining momentum as they follow a precise recipe to define the strength and corrosion resistance of the new metal. Even the fumes and industrial dust generated during this intense thermal process are captured by multi-stage filtration systems. This does not only function to reduce atmospheric emissions, but also allows for the recovery of valuable subproducts including lead, tin, and zinc. The equipment gradually purifies the environment while reclaiming secondary materials. The metal now exists in its most refined and purified state. The liquid stream is stabilized and ready for the final transformation. But how does the system turn this river of fire back into a solid and usable form? The molten mass begins its transition from the furnace toward the casting station without haste.